This week we're going to go into planetary scales, circulations, or the atmosphere as a whole. We put together each of the variables that contribute to these circulations over the last several weeks. Each variable constitutes a part of what makes up our weather. And when you look at the planet as a whole, and I'm not looking down at the single cold front or a single station, I'm looking at it as a whole planet. We can come up with some planetary scale features that we're going to deal with here. And these planetary scale features are really kind of define what the weather is going to be like over the long term where you live. So if we had a non-rotating Earth, obviously one side would be really hot, one side would be very cold. We don't. Thank goodness for that. But think about it. If you did, hottest, most direct sunlight would be over the equator. Air would rise there. Coldest, back on the other side of the world, air would sink, and you would just keep that circulation. But we have a rotating Earth. And because of that, the speed at which it rotates, we have three distinct belts. Winds blow towards each other at 0 to 30 degrees, 30 to 60, and 60 to 90. And they kind of define an overall climate for the atmosphere. So where the winds come together, like at 30 degrees north, there's high pressure. Where they come apart, at 60 degrees north, there's lots of low pressures that go there. And where we come into, down by the equator, the intertropical convergence zone, is another area of low pressure. And they just look up and down that way. There used to be sailing ships that went from Europe to the United States, and they would try to stay away from 30 degrees north. One of the reasons was, right along there, the wind is so light, because of it's under high pressure, you don't have much pressure gradient, you wind up not going anywhere very much, maybe in the doldrums. So here you can see, and because of our Earth being tilted, that 30 degrees north high, it's going to be a little further south in the winter and a little further north in the summer. So everything moves according to what season it is. And along that 30 degrees, there's a lot of warming. Very clear skies. Typically, a lot of major deserts are located on the eastern flanks. Eastern flanks is where the wind's coming out of the north, clockwise rotation, and it's sinking air. Poleward of these, you get a lot of the westerly flow. We live in the westerlies. So that's where we are, just north of these high pressure systems. And further north, you have highs over top of the North Pole, over top just to the south of the North Pole. And we have a circumpolar vortex that literally gets very intense in the wintertime, either the southern or northern hemisphere. And this kind of controls whether we get Arctic air or not. So you can see we have a wavy mid-latitudes, trough and high pressures. And because of that, over the Arctic, above 60 degrees north, the polar tropopause is fairly low. Down to the south, between 0 and 30 degrees north in the tropics, tropopause is fairly high. We know that's because of temperature. However, between the two is where most of the temperature change occurs. And here, we can really fluctuate on the tropopause height. And there is an inversion right down by these trade winds, which occur around these subtropical highs, which suppresses, makes convection, and keeps the air very clear there. The intertropical convergence zone, that's right where the southern hemisphere winds converge with the northern hemisphere winds. They move north and south, depending on the season. Notice they don't move a lot over water necessarily. But look over land. Wow, that's a lot of motion up here because of the land. Why is that? Because the tropics water takes a tremendous amount of heat to warm up. Land, on the other hand, does not. So because of that, the land changes temperature a whole lot more than the summer. And because of that, we have what we call the monsoons that set in. You saw the intertropical convergence zone move north of India. Well, guess what? If it moved north of India, then it's getting southerly flow into it, and you wind up with a lot of moisture coming out of the Arabian Sea into the Indian Ocean and into India itself. Lots of rain. Same thing holds along Southeast Asia. But in the wintertime, everything's further south, and you wind up with having a lot of extremely cold air and dry air coming out of the middle part of Asia. So these are types of monsoons, wind patterns that just persist for months at a time. And these planetary scale circulations, if depending on which side of that subtropical high you're on, depends on what your weather is going to be. San Diego and Charleston, South Carolina are about the same latitude. San Diego is on the eastern edge of the Hawaiian high. Guess what? It has northerly flow, sinking motion. Charleston is on the western edge. It gets moisture out of the tropics coming into it, lots of rain. And here you can see, because these highs are so persistent, they actually create circulations. And here, for example, is the North Atlantic Gyre. Guess what? The Gulf Stream comes up through Florida, the Strait of Florida here, picks up right here, and part of the North Atlantic Gyre is part of the Gulf Stream. So they flow together, and they even come over in towards England, which keeps England a little bit warmer, actually, than it might otherwise be. We have a monsoon in the United States called the North American monsoon. What happens in the summertime is you get a lot of heating down here. There's actually some higher ridges down in this area of Mexico that heat up in the summertime. High pressure forms a loft with that heating because we've said the pressure drops slower when the air is warmer. So you wind up with high pressure aloft, low pressure at the surface. What you do is bring in moisture, then coming off the Gulf of Mexico or coming up around the west side of that high, and you get lots of moisture and lots of rain. That's when the rainy season is, down in Arizona, New Mexico area. Rossby waves, they are, looking at them, let's just take a picture of one here. Might be simpler just to describe it, what it looks like. Here is a Rossby wave. Kind of confused, aren't you? Look at this large area of low pressure. What do you see? Kind of the height pulling away from the large area of low over the Pacific, another one over the United States, central North America, another one pretty much near Greenland, and another one here. These are Rossby waves. They're, instead of little tiny waves in the atmosphere, these are big waves. They kind of control, they don't move real fast, so they control where dips in the atmosphere. Because we have a Rossby wave over North America, we have a dip, which is causing all the cold weather in the eastern part of the United States. Here is to the west of that, have a ridge of high pressure, warmer weather. So that is a Rossby wave. And we can move forward from that. You can see the zonal flow. We just looked at very meridional flow over the U.S., more zonal flow over the Pacific. Zonal flow means there's temperature contrast or broad. Meridional flow, you think about it, you're pulling a lot of Canadian air down to the United States and bringing a lot of the warm, moist air out of the tropics to the Gulf of Mexico. They're when the bigger storms develop, more contrast. And here you wind up with blocking patterns. Sometimes these set in, and we actually have almost that right now, slowing down, keeping the cooler air coming down out of Canada and the warm, moist air coming up to the just off the Atlantic coast. And these can persist for months sometimes, but this time they're not too long. And this is a similar blocking pattern that occurred during the summer of '93. What happened was record rainfall. It just didn't move anywhere. You can see that there. All right, a polar front is a narrow transition zone between cold and warm air masses. All right, so higher up in the atmosphere, closer to the tropopause, there is extreme temperature contrast if you go north to south many times. That temperature contrast causes there to be a pressure gradient. That is what causes the jet stream to be so powerful up in that area. The Coriolis effect plays a role in that jet streak, of course. And you can see there's a seasonal shift to the jet streak. Guess what? It's further south in the winter, further north in the summer. Not unexpected. Along that jet streak, along a Rossby wave, there are shorter waves. And where these dig down, they may have convergence, which actually, think about it, convergence aloft, winds are flowing together aloft, pushing downward, they create high pressure. So on the west side of these little troughs, you find mostly high pressure. On the east side, winds are speeding up, pulling apart. You have divergence aloft, winds are pulled upwards. That's where your low pressure is going to be. And you can see that right here on this. And you can see here's a typical jet streak and various divergence in the left front quadrant and the right rear quadrant. El Nino is part of a global circulation. El Nino is looking at the Pacific Ocean and seeing if temperatures are above normal or below normal. It was developed actually and discovered by fishermen in Peru. Certain years they could catch certain kind of fish. Other years they didn't catch hardly anything. And they discovered it was because of this temperature change. The fish moved depending on how the ocean temperature was. So El Nino, temperatures are a little warmer than normal. La Nina, temperatures are colder than normal. We are currently in a La Nina phase. As a matter of fact, this is the third year for La Nina. Very unusual. And you can see them here, how they translate. This El Nino and La Nina are impacted by the oceans and by the atmosphere, so they're a combination. Ekman's spiral. I don't know if any of you ever been to the Outer Banks. That's where I experienced it most, and it can happen even in Virginia Beach. But what happens is if you have a south wind up along the coast, the water will start turning to the right, like we would expect. Coriolis effect. Well, as it's turning to the right, it's turning away from the coast. So what happens? The water down below wants to come up, and as round this water that keeps turning to the right continues to turn and sink. So you wind up literally pushing the water at the lower elevations upward to the surface. And what happens is water temperature drops ridiculously. There have been times in the Outer Banks I have seen water temperatures in the low 80s one day and in the mid 50s the next day because of this Ekman spiral. It occurs also at the equator as well. Here you see El Nino, warm phase. Here you see what happens, a lot of convection, much stronger winds closer to the equator. La Nina, opposite, colder, more of the convection and stuff further north and west. So you wind up with weaker winds down in the tropics, not as strong of an easterly flow. And that's actually why hurricanes are more likely during a La Nina than an El Nino. And because of La Nina, most of the storms come in further north on the west coast of the United States. That's why California has been so dry. North Atlantic Oscillation is a seesaw circulation between the subtropical high and the polar low over Iceland. So that is another impact that you find here. And it can really affect the eastern part of the United States. Positive, which means there are stronger than usual wind blowing across North Atlantic. Colder air masses move east. Milder, wetter winters and summers over Western Europe. When it's negative, you also get cold weather more into the Midwest, Mid-Atlantic, and way better chance of above normal snowfall for those areas as well. So if you're a snow freak, you want a negative NAO. And here you can see NAOs have a major impact on how winter will be, depending on how they are. So it is interesting. If we could forecast NAOs fairly well in the wintertime, we'd have a much better chance, at least in the eastern part of the United States, of forecasting winter temperatures and precipitation totals. We do not do a good job of that. the Arctic Oscillation. All right, the stronger the winds are in the north over the poles, they kind of stay there. It pulls the Arctic air in, keeps it there. When they begin to weaken, there's more of a variation in pressures. Some of that cold air then can sink south. So when the Arctic Oscillation gets lower, we wind up getting more cold Arctic air in the United States. When it stays very cold, we have the other problem. And here you can see the positive and negative phases of that. And there's also a Pacific decadal oscillation as well. And there's phases. The Madden-Julian oscillation. It was discovered maybe 15, 20 years ago. It's actually a fairly recent discovery. What it is that over the Indian Ocean, the extreme western Pacific, you wind up with huge convection that sometimes forms. This convection triggers literally like a wave impulse in the atmosphere. And as that wave impulse rotates around the Earth, that is caused by this Madden-Julian oscillation. It can take 30 to 60 days to go around the whole Earth. And as it's doing this, that pulse will help high pressure form and low pressure form, depending on which phase of that pulse you're in. So this can help cause more rainfall, or it can suppress the rainfall. It basically really enhances the pineapple or atmospheric rivers into the western U.S. So that's about all I really have with this. I want to show you just the current image or whatever of, here's a subtropical high pressures. And here you can see really a strong cold front up in here coming in, cold air coming down out of Canada. So hope you got something out of this. Here you can actually see the temperatures are actually in the 20s up in Canada, low 20s during the day. So hope you enjoyed that, got some information from it. Let me know if you have any questions.